It's very difficult to teach obeying rules that you have to start at 3:30. I am not a person that is good with following rules, so my apologies. All right, it's 3:30. Welcome back. A few things that I wanted to say. The notes are, I'm going to try to have the final notes maybe the morning of the lecture day. So on Monday morning, you can just download and read. The notes are not for printing them. Really, they are for looking on the, on your computer, and they contain enough information that you don't have to go and look over many books. Okay, so it's very possible. Like today, I may skip 50% of the slides. The anticipation is that you guys look at it to know what it is there, where to find information when you need for your homework or projects and things like that. Now, the video is also there, but there was obviously some technical issue because it's not coming in the form that it was expected to. So hopefully today that issue will be fixed as well. We will know. Okay? All right. So I have about 130 slides to tell you in the next hour, but they are all sort of very basic, nothing really to memorize, but there are things that you will need to look constantly as you do analytical calculations, at least with Bayesian inference. Okay. So I wanted to very fast discuss some distributions, and the purpose of these distributions, lots of them will be used for prior models when we start doing Bayesian analysis. All right, so you will, you don't have to memorize the details, what's the mean and the variance, but when you see a form and it screams at you and says I'm a Bernoulli distribution, you should know what a Bernoulli distribution is and where to look. Like even myself, when I have to look at lots of these things, I hit Wikipedia and there is the Bernoulli distribution with everything you want to know. So, a Bernoulli distribution, you can think of the classical heads-tails experiment, heads being 1, tails being 0. So you throw the coin on the air, and the probability of getting heads is mu. And the probability of course, tails 1 minus mu, and x is a binary variable, takes values 1 and 0. Now, the best way that I like writing the Bernoulli distribution is using the indicator function. So, it's a good idea to get used to it because this is way much more precise than this expression. This tells you when x equal to 1, this is 1, so the probability is mu. When x equals 0, this is 1 minus mu. So it's more elegant way for writing this type of calculations. Okay, I don't have to, as I mentioned, you don't have to memorize this, but when you start using this often enough, you will know that the mean of the Bernoulli distribution is mu and the variance is mu 1 minus mu. And then you get this very nice form for what we call entropy, that we'll discuss this later on, that some of you, especially from physics, you may recognize from statistical mechanics context. Okay. I have not said anything about the likelihood function, but assuming that some of you know what it is, so let me throw this and we will come back to it next week. Suppose this coin experiment, you conduct it n times. So you conduct it the first time, maybe it comes heads, so this is 1, maybe this is 0, 1, whatever. So you conduct it n times. And the likelihood function basically is what's the probability of having these observations, and we assume these observations to be independent from each other. I mean, when you throw the coin, every time it's another experiment. So the likelihood is what you see here, is the probability of having observing in the sequence of these experiments the data x1, x2 to xn. So you notice if you take the binary distribution that we had before and you multiply this for all data sets, effectively you get an expression that looks like that. And what is m? Before I press the button, what is m going to be when I write this product as mu to the power m? what is M going to be? The number of times that in the N trials I observe heads, all right? So, okay, so we can extend, so this was these binary experiments that we conducted N times, but we can actually do this a little bit differently. Let's say we conduct N experiments, a very specific number, and in N experiments we want to have M heads. So the probability for having M heads in N experiments is basically given by the binomial distribution that, except this coefficient on the front, it's identical to what we described before. A parenthesis, since I see here lots of little MATLAB programs. The book by Murphy on machine learning that I linked in every lecture, on every slide, more or less, has a MATLAB software that reproduces lots of very easygoing results, and it's extremely easy to install. No error bugs or anything like that. It's the third version of the software. I recommend it because a lot of times, to understand some of the calculations, if you look at the program, what it does, you may get insights that otherwise you will be missing. Okay? So some of the other software, for example, I'm not quite sure, actually this is a little library written by another student in another offering of the course. And maybe another year from now, one of your solutions to the homework will be linked somewhere there. And so you will remain in history for as long as this course is around. Okay? And that's why I'm asking to write nice software so I can copy it free of charge. Okay. For this binomial distribution, if you want to derive the mean and the variance, rather than doing calculations, and I imply here what type of calculations you may need to, you can think, if you're gonna, in N experiments, you want to get M heads, right? This is really the binomial, this variable M is the sum of N binary variables, where you get for each of these experiments heads with probability M, tails with 1 minus M. So the expectation of M in the Bernoulli distribution is N times mu, and the variance is N times mu1 minus mu. So you don't have to do calculations on that. Okay, generalization. So things will get a little bit more interesting now. Suppose rather than having an experiment, a binary experiment, you have a variable that can take one of k values. So this is one of k coding, as they call it. So at every time you do the experiment, one of these variables will take the value 1, everything else will be 0. Okay? And we will call the probability, let's say that the kth value will be 1, mu k. So this distribution, which is generalization of Bernoulli distribution, looks like what you see here. And again, try to get used to this notation. So we have k states. Each of them, you get heads with probability mu k to a power xk, or even better, right? This is the preferable notation, mu k to a power that is the indicator of xk being equal to 1. Okay? Now, this distribution has the constraint, of course, that all of this, the sum of all of these probabilities has to be 1. I mean, if you do the experiment, you have to go in one of these states, so these probabilities have to sum to 1. Okay, you can show trivially what the mean and the variance is, using generalizations from the Bernoulli distribution, so I'm not going to go to that. This distribution, by the way, in other domains, especially in computer science, you may see it as a categorical distribution, and it comes with different names. Okay, so you can use to the fact on how to write the likelihood from data that come from different distributions. So let's take this multi-Nulli distribution, and let's assume that we conduct N trials, N experiments. So we conduct N experiments, and every experiment we're going to go to one of the states. So I write here the likelihood of observing data x1 to xn according to this nice form here. All right? So why do I write first that the likelihood of this data is the product over all the data sets? So what does this imply? That every time I do the experiment, it's an independent experiment, okay? And what is this? This is basically what we discussed before for the probability of one trial. So, and the only difference here is because this second term here refers to data point n, instead of xk, I use xnk to emphasize. So what is xnk? So x and k, so it refers to the end point, all right? And k refers to the kth state. So when this is 1, which means if on my nth data point I go to state k, this will be equal to 1. Otherwise it will be 0. And the reason I use a product here is to account for all of those terms, but only one of those terms will give me mu. The other term will give me basically 1, will be mu to power 0. You see that? So basically from these terms here, for each point n, I'm going to have only one active term. Everything else will be 1. Okay, so I can actually take this term here, move it outside, put the product inside, and then write this eventually as the product of all possible states of mu k to a power mk. And what is mk? I mean, we just, you know, you can use common sense basically in the notation here. What will be mk? So it will be how many times in my end experiments that I conduct, I'm going to go to state k. That's all. Okay. As I mentioned, we will discuss maximum likelihood later on, but since we discussed about different distributions, it will not hurt you to see certain things twice or 3 times. So here, if you refer to multi-nully distribution, someone will tell you, can you give me some estimate? So if you do a lot of observations, can you give me some estimate of this probabilities mu? How do we estimate those? And the idea, and this is sort of not a Bayesian way, the idea is to use what's called maximum likelihood. Basically, we had the likelihood before of the observations. Now we will try to find the mu that maximizes the likelihood of the observations. Okay? And instead of working with the likelihood, I have the log likelihood, but you notice I use another extra term to enforce the constraint that the sum of the mu's is equal to 1. So if you do the algebra, it comes out that the answer for mu k is the expected common sense answer, that the probability mu k is basically the number of times that I will hit state k out of n experiments, exactly as you expect. Okay. Generalization now on this one in k coding is this multinomial distribution where you conduct exactly n experiments. And in this n experiments, m1 times you hit state 1, m2 times you hit state 2, and mk times you hit states, the state k. So this is exactly what we had before, times this coefficient that most of the times is not relevant. Let me bypass this. This is an example from biosequence analysis. For those in biological science can read it. It's sort of a direct application. This, we don't need it. All right, so let me introduce, because we will need this later on, the concept of the empirical distribution. So we have some distribution from where data come, but we don't know what a distribution is in general. Okay? So a way to denote a distribution, and I'm actually, to avoid taking you through the whole slide, let's look at the bottom. So let's say you take samples, little xi, from some distribution, but you don't know what a distribution is. This is what we call this summation there with these delta functions and the coefficient 1 over n is what we call the empirical distribution. Okay? It is an approximation of the actual distribution, but is defined completely by the observations. So it's a lots of delta functions with weights 1 over n. And later on, we will also see a similar empirical distributions, but written with some weights that may not be 1 over n, but they are also, if you sum them, you get 1. But for now, the empirical distribution of samples that they are, we sample them independently with an identical fashion is 1 over n times these delta functions summation. Okay, so let's let's say somebody gives you a function f of x and tells you, can you find the expectation of that function under this distribution? Now, you don't know the distribution, but you have observations of that from that distribution. So what you're going to do is, rather than using an expectation with respect to the exact probability from where x comes, we use the empirical distribution instead. And what it comes out, you see the typical result that you may have seen with Monte Carlo approximations. You get 1 over n times f of xi. You remember, if you integrate a function with a delta function set at a point, you get that function at that point. All right? So this is an interesting result, right? So it tells you if you approximate the distribution with the empirical distribution, then the expectation of any function of x is basically the sample mean of x. Okay? The sample mean of x. All right. Some more complicated distributions that are essential actually for lots of things in Bayesian analysis, and that's, to start with, is the student's t distribution, an interesting name that has history that I never bothered to read about. So this is for a univariate student t distribution. It is important to always, when you have something that looks like this to some power, to always think of a student t distribution. But I can tell you, you will never get this coefficient in the exponent and this nu here to match exactly. So you have to manipulate whatever expression you have, if it looks remotely like this, to put it on this form. So don't expect something will come and say, I'm a student's t distribution. It will not. You make it to be, if it looks like. All right, so this distribution has, lambda is called the precision. Precision means 1 over the variance, but actually this is not true. In general, lambda is not 1 over the variance of this distribution. Unless we will see you take the limit of this coefficient nu to go to infinity, and in that case the distribution becomes a Gaussian, and lambda is indeed the precision of the distribution. Now, the reason we're interested in this distribution, it looks like Gaussian actually very often, but it has fat tails. All right? So I have a number of proofs that you may want to read, you may not want to read, but they're essential to get an idea, for example, why and when this distribution looks like a Gaussian. The derivation is actually on this slide. There's really nothing more, so you may want to look at it. So let me give you some plots. These are for different values of the coefficient nu on the degrees of freedom that you have, and you always notice that the tails here are much fatter than the tails you get from a Gaussian distribution. I believe there is a plot, maybe in the next slide. Yes, here it is. So this is, I want you to look carefully on this slide. I have not defined the Laplace distribution yet, but it's plotted here. It's coming in a slide or two down the road. But let's compare the Gaussian distribution with the student t distribution. So this is the Gaussian, and you notice the student t distribution, the tails are much fatter than the tails of the Gaussian. This has lots of implications, and I have an example coming that I will show you one of those implications. And the other thing that sometimes creates problems, if you take the log of, let's say, the Gaussian and the student t distribution, you notice the log of the student t distribution is not concave. All right, so when you hear that, that may have implications because lots of times we will need to do optimization, and we would like, for example, minus the log of this to be convex, but here, unfortunately, for the student t distribution, that is not the case. So, from where is the student t distribution comes and why it's important, okay, to just have it as a special distribution? Well, here is from where the distribution comes. This is an extremely important formula. You don't need to remember it, but you need to remember what the formula implies. So, to get a student t distribution, this will come to be a student t distribution, what you need to do is, you need to average an infinite set of Gaussians, univariate Gaussians. And you average them with weight that is a gamma distribution on the precisions of each of these Gaussians. So it's basically, you say, I'm going to take Gaussians with different precisions, and I'm going to find the average of those. This is what it is. And what it comes out from this is a student t distribution. So effectively, it's like taking Gaussians with different length scales. All right, this is another way to think of this precision, and averaging over these length scales. And that gives you a student t distribution. Now, I have not yet defined what the gamma distribution is, so here is how the gamma distribution looks like. Of course, you will see it so many times in this course that hopefully this term here will become something very familiar. Okay. So I'm actually giving you a derivation why this indeed gives you the student t distribution. So you have to believe that things, right, take a few lines of derivations, and when you do them, nothing is magic. You don't have to search. The slides contain the proof of why is that the case. All right. So let me explain why these fat tails of the student t distribution are relevant, and we will see this in the context of Bayesian analysis in forthcoming slides. So let's say you do some observations, and this is a histogram of the observations, and you want to fit some distribution on them. And you can think for now that you're going to fit this by, so let's say if it's a Gaussian, you have to find the mean and the variance, and the easiest way is to find the maximum likelihood estimate. So find the mean and the variance that maximize the likelihood of these observations. So if you do this for the Gaussian and you do this for the t distribution, effectively you get two distributions that look very close to each other. That's why, very often student t distributions is perceived to be like nothing else but another Gaussian. Well, of course, we know that it is an average of Gaussians over these length scales. So in this case, it makes no difference if it is a student t or a Gaussian. But let's see at this picture what happens. We have more or less, let's say, the same histogram, but we have an outlier. So one of the data points was way out there, obviously wrong. Okay? So if you try to do maximum likelihood estimation and you compute the Gaussian and the student's t distribution, so here is how the Gaussian suddenly looks like. So obviously it was pushed way down towards the outlier. That's not good. But the student t distribution was very robust and basically did not change because of the presence of outliers. Okay. So that is why it is very important for this sort of problems. Okay. We don't need this. All right. So let me rapidly, I already showed you, well, I don't know if, no, actually I showed you the gamma distribution. This is the beta distribution. So this will be used as a prior distribution in a lot of semi-analytical calculations we have to do. It comes up practically in every lecture until the end of the semester, so it is a good idea to remember this expression, x to the alpha minus 1, 1 minus x to beta minus 1. Obviously, it's a univariate distribution. And I am giving you here some plots for different coefficients, alpha and beta. And you will see that, for lots of different combinations of the coefficients. This is a one-mode distribution. But when alpha and beta is less than 1, you notice you get 2 modes at the edges. So if you're going to use this as a prior, right, you want to think, what do you want to do? Do you want, for example, to give priority to the 2 edges of the distribution? Then your alphas and betas have to be very small. If you want to give something that is, let's say, in this case, uniform, alpha equal 1, beta equal to 1, you select that. If you want your mode to be slightly towards the left or the right, you can manipulate these coefficients. Mean and variance and all of these things you can read on the web, you know what the answers are. All right. And lots of proofs there. So this is the gamma distribution. This is the distribution we use for modeling length scales and precisions. It looks like x to the alpha minus 1, e to the minus beta x. This is a rate parameter. This is a say parameter. Names don't mean very much. This is the gamma function. Let's see if we have a plot of this distribution somewhere. Yep, so this distribution looks like this. So in this case, we had a histogram and we fit into a gamma distribution, and that's a nice fit. Okay. Now, if x is a gamma distribution, x inverse is what we call an inverse gamma distribution, and an inverse gamma distribution looks like that. Now, if we said that x, we use it to model precisions, which is the inverse of variances, when do we use the distribution x minus 1? So if x is good for modeling the precision, what is x minus 1 good for? What's 1 over the precision? The variances, okay? So which one you use, actually the calculations will be identical. The algebra will be easier if you use one or the other, right? So you have to choose this properly. Okay, don't have time for this, you guys read more. Okay, so let's go fast, put all of these things up, not too fast. So we have 2 random variables, x and y, and now we look the probability of 2 events where both x and y participate, and that leads us to define basically the joint probability density function p of x and y, exactly as we did for univariate random variables. Independence, you remember we discussed independence for events. Now, and I don't give you a proof, independence for random variables can be written in terms of the probability density function as p of x and y equal p of x times p of y. That implies independence. It's not a trivial derivation, but you can think if you multiply this with a domain of x and you multiply this with a domain of y, then you can transform this to actually probabilities for probability densities, and then you can get rid of the domains and you get this thing on the limit with densities, okay? But it requires some sort of derivation. The covariance, you have seen it in undergraduate courses, is basically the expectation of this expression that you see up there. And if you expand this, you basically get the covariance being the expectation of x and y times minus the expectation of x times the expectation of y. Now, often, we will use basically the way we will pre-process data. Sometimes we will normalize data, and the way you normalize them is removing the mean and dividing by the standard deviation of each of these variables. So you may have seen this before, and also you may have seen a normalized version of the covariance for 2 random variables, which is called the correlation coefficient. So the covariance of x and y divided by sigma x, sigma y gives you the correlation coefficient. So if you want to plot it, this is the variable to plot. you can define this for any function of x, for any function of y, all right? And now this covariance in some sense is it sometimes can create a confusion because it has nothing to do, if it comes out to be 0, has nothing to do with independence of the variables x and y. And I will emphasize this throughout the course, right? The covariance, as you see, involves expectations. So being 0 in expectation is one thing. Being 0 in probability, it's another thing. That's what independence is. So try to separate this being equal to 0 with independence of the random variables x and y. This is a much more general expression. Of course, if independence happens, then this comes to be equal to 0, but not the other way around. And most probably that's what this slide says. All right, so I'm going to bypass it. You can define the cumulative distribution functions for many variables, exactly the same way we did for univariate random variables. Okay, so this is the CDF for n random variables, and of course the PDF can be seen as the nth derivative with respect to x1, and I see a typo there, x2, xn. All right. So if you have a vector random variable, and practically everything we will be doing in this course will be with vector random variables, you can define the covariance of this vector random variable exactly as we had before. So x, this is for continuous random variables, x minus x times x minus x transpose, p of x dx. You can, if you want to take component-wise this, you can write simply another nice ij components here. You can show with one line of derivation that the covariance for this random vector is a symmetric semi-positive, semi-definite positive matrix. Both of these properties are extremely important because the symmetry implies that basically you have to keep track of very few, if you have a huge vector x, you don't have to keep n squared type of variables to record down what the covariance is, right? So for a symmetric matrix, what do you need? What's the calculation we're going to give you? Most probably n times n plus 1 divided by 2, I assume, okay? So that is very important, and of course, the fact that this is semi-positive definite has lots of implications, otherwise we'll not be able to do sort of any calculations. In this covariance, if you take the diagonal, no accident, all right, it comes up to be the variance of its variable. And this last equation, when you look at it carefully, when you go home, is basically a good exercise on the marginalization of multivariate random variables. So in matrix form, this is how the covariance looks like, okay? Nothing unusual. So if you have two variables that they are linearly related, all right? So if this coefficient is positive, the correlation coefficient comes to be equal to +1. If this coefficient is negative, the correlation coefficient comes to -1. But, this is as much as you can extrapolate from the correlation coefficient and this linear dependence, because most data, they are not linearly dependent. And there is a very nice link on the web that has this very nice picture that shows you why the correlation coefficient, it is very often wrong. Okay? So for these data sets, in some sense, the correlation coefficient, you can see here the data linearly related, all right? The slope is positive, so the correlation coefficient is 1. Here it's 0.4, so this makes sense. But then you look at this highly correlated data sets, all the correlation coefficients basically, they look the same, 1, -1. This is undefined because there is no variance in y, so you get infinite basically. And then you get all of these weird things, correlation coefficient of 0, but the data sets are extremely highly correlated, but non-linearly. Okay? So don't, make conclusions, say, oh, these are correlated, Correlation is good to make some comments as to the linear way of relating these variables, but if the data sets become nonlinear or very highly correlated, this is not the case. All right. You know what? I did not derive this equation on the top. So you remember this equation here? So what does this equation remind you from the first lecture? That's the product rule, but here it is written not in terms of the probability of events, but in terms of density functions. Okay? So for continuous variables, we will use it like that. And the derivation, actually, it's one line, right? If you take events and you make the domain where these events happen to go to 0, effectively, you can go from probabilities to probability densities, and that's how the derivation comes. Okay? So not only this expression, we can write it down, but we can write Bayes' rule in terms of probability density functions, and there it is. Okay? So again, not necessarily a trivial outcome, right? It takes a few lines of derivation, but Bayes' rule, you can write this in terms of density functions in exactly this form. So you can invert here from x and y to y and x, and we discuss about this term also in lecture 1. All right. I am only going to go directly to the result. The derivation is in the notes. And I'm going to discuss the computation of expectations of random variables in terms of conditional expectations. So if you ask what's a conditional expectation, right, you can look inside this integral here only. This is the expectation of x, but with y given. So the density that I'm using here is the probability of x given y, right? So this is the conditional expectation of x given y. And here is what we're interested. To compute the expectation of x, if it is easier to compute the expectation of y, then the only thing you have to do is average over all possible values of y with the probability of y. This comes very handy, in particular for calculating variances, not just expectations, okay? And we will see that expression as we go along, okay? So again, the expectation of x is the average of the conditional expectation averaging with respect to y, okay? A very useful formula. All right, so we jumped hundreds of little topics, so you can see these things from as a review from your earlier courses. This is a multivariate Gaussian distribution. Here we have d degrees of freedom. x0 here, the way I denote it, is the mean. This is the variance. Sigma minus 1 is the precision. Symmetric, positive definite, as we discussed this in general. If it is symmetric, well, I mentioned before, d times d plus 1 over 2 elements to describe it. And if you have a linear combination of two independent Gaussians, so if you take, let's say, ax1 and bx2, and this is very important, and these two Gaussians are independent, you can actually, this is still a Gaussian. The mean is the average of the means, but notice the transformation for the variances. Okay, AA transpose and BB transpose. Now I have a question for you. If x1 and x2 were not independent, is any of these two terms for the mean or the variance still correct? Where is the independence? In what part of the derivation from the left to the right you think we need the independence? In the variances. So this linear relation with the means, it is valid regardless what, but this thing for the variances requires this independence. Okay, lots of nice plots. You may think that these are trivial, but you will have to write some code to do these nice plots for your homework sets. So it may not be a bad idea to actually consult on how these plots work, because your plots have to look as good as this, if not better. All right, and I want the better, so next time I use your plots and I get rid of this. All right. Very important topic. Suppose that we are given, let's say, the distribution of the probability density of a random variable x. So I give you p of x, and I do some transformation, or actually, here it's actually the other way around. Okay, I give you a distribution of y, p of y, and I do a transformation with some function g, x, g of y. How do you transform? How do you come up with the density of x given the density of y? I mean, you don't have to read what it says there. So how do you, when you change variables and you transform them, how do densities transform? So do I take, for example, the probability, here I don't know, I wrote it like that, doesn't matter, it's the same thing. So do I take the probability of x and I just plug in, instead of x, g of y, and that's the probability of y? Obviously not, because I see that there is an extra term there. So what does this equation implies? If you put dy on the other side and you keep dx on this side, what is the trick here to do the derivation? That when you transform a variable, what do you need to preserve when you go from x to y? So the probability mass in x, right? So if you look at interval dx and you look at interval dy, the probability mass in x has to be equal to the probability mass in y. This you can think as the change of volume when you transform from the x domain to the y domain, or something like that. And of course, you can do this in high dimensions as well, but this is in absolute value. That's why you will see this coefficient s when I use this derivative, g prime of y. So if this derivative is negative, I'm going to put s equal -1 to make it positive. Okay, so it looks like that. Now, I'm going to give you an example on why you need to be careful with this, because these transformations come often, and sometimes when you try to do the algebra, you'll be wondering why things don't come the way that I have them. Sometimes there are cancellations of variables that account for this transformation of probability distributions. Sometimes you see them, sometimes you don't see them. But look what happens here. Let's say we have a Gaussian, and this is, I transform the variable x to a variable y through this function. So this color here variable, I'm not very good with colors, okay, whatever color it is basically transforming this distribution directly to through the function, y equal g minus 1 of x. All right, and you notice, the modes of the two distributions match. And this other one is basically taking all the samples in the histogram of p of x and transforming those samples to a histogram of p of y. And you notice the modes of the two distributions don't match. Okay? So again, the reason they don't match is because when you compute the probability of y through the probability of x, there is an extra term, and that, when you try to find the mode of the distribution of x and the distribution of y, will be affected by this extra term. But if you do it with Monte Carlo, you are safe, And sort of this is the calculation that you see here. You can construct a histogram and then map each of the samples, and you will get basically the correct distribution. All right. We're making progress, but I don't think we will ever go close to where I want it to be today, but it's Friday, so we can survive. So you remember the student t distribution. Reminder again, we calculated, we didn't do the derivation, but I told you, you take an average of Gaussians with different precisions, where these precisions are averaged with the gamma distribution. All right, so you take all possible taus, where taus are governed by a gamma distribution. This gives you a student t distribution. When you do the algebra, and it was given in an earlier slide. So the question is, how do you generalize this? How do you generalize this to come with a multivariate student t distribution? And that you don't actually have to search a lot in the literature to find the actual calculation. So I'm only going to, it's discussed in the slides, so you can read on the details, but the actual calculation is what you see on the bottom. So effectively, you keep this gamma distribution univariate as we have it up there, but you notice here, because the Gaussian has to be multivariate, the precision of the Gaussian is some coefficient eta times some matrix lambda. So we keep lambda fixed, and then we integrate for all possible etas. So you can think, that you move this concept of length scales on a scalar variable, and you average with respect to that scalar variable. So if you do that, you come up with the student t distribution for in the multivariate setting, and all the things we discussed before about fat tails and looking like a Gaussian, and on the limit of this coefficient nu going to infinity approaching a Gaussian, they are also true for the student t distribution. Many times you do lots of calculations with Gaussians, but at the end of the day, the result comes not to be a Gaussian, it's always a student t distribution. Okay, so this is going to be a very helpful type of calculation. Now you may say, if this is a computational course, why do I care about analytical calculations? Well, can you imagine that, let's say your posterior distribution in your particular problem of interest has an analytical expression, and you go in discussion about numerical exploration of this and that, and there is not exact expression, and I built this algorithm. Well, what algorithm? If there is an exact expression, that's what you use. So you need to be sure to identify if you can come up with closed form solutions, because this can, if you can think if this X is 1,000 or 10,000 or a million dimensional, it's nice to know that it fits on a student t distribution. Okay, the derivations for the mean and everything else are given in the notes, so those, when you need to use them, you use them. Okay, one more distribution, and this will be very useful for non-parametric statistics, very essential for a lot of modern applications of machine learning, and this is the Dirichlet distribution. So it's, of course, a multivariate distribution, has a vector, alpha's parameters. So it looks like that. So the probability of mu given alpha, all right, is very similar to this multi-nully distribution we had. So these are the distributions, mu k, but also this coefficient alpha tells you that each of these event k happen alpha k minus 1 times. So again, it's like having k events, all right, and each of these events was observed alpha k minus 1 times. And the same constraint we had before, that the summation of these probabilities is 1, is holding here. Now, you may say, where is this distribution going to be useful, right? Well, you can think, for example, in a multinomial distribution, this can be very handy You remember the multinomial distribution was looking mu k to mk. So where are we going to use it if my observations come from a multinomial distribution? How this can be useful? I'm extrapolating now. You remember the multinomial distribution, we do n experiments and we observe, let's say, event k with probability mu k, mk times. So we had there a term mu k to the power mk. So where do you think this can be useful in that scenario? Well, it would be useful because we can use this density as the prior density on mu's when the likelihood model, the observations come from these multi-nully distributions. Okay? And actually, this will fit in with this concept of conjugate priors, because if the observations were mu k to the power mk, you can see that the posterior distribution will have exactly the same identical form as the prior Dirichlet distribution. Okay, so I'm giving you this ahead of time before I said anything about priors and posteriors, but you know, it is not a bad idea to know where these things may relate with other things you heard in other courses. So this distribution is k-dimensional, but in reality, because of this constraint, the summation of this mu k's being equal to 1 is really k minus 1 dimensional. So when you try to do calculations like integration, you may want to get rid of this constraint, all right, and do the integration in k minus 1 space. So for example, in 3 dimensions, this is where this distribution varies, right? On this triangular that in the mu1, mu2, and mu3 space. The expression on the bottom, I'm not going to even tell you because we're not going to have time, is an extremely important derivation that is going to be used in many calculations throughout the course. So I will remind you this as we go along when it is needed. But you may want to, the derivation is actually, it looks complicated, but this will be handy. It gives me the expectation of the log of mu j, all right, so this will be a useful calculation. I'm giving you lots of derivations, so things don't look weird. I discuss that the Dirichlet distribution can be useless prior to the multinomial. So this is the derivation that I was telling you before. You don't know we have the slide, so okay. And this is how the distribution looks like, and in 3 dimensions. And the interesting things you can get if you play with this coefficients alpha. So the space, obviously, there are 3 variables, but we get rid of the third, so we can plot this on the plane like that. You can see that you can go from a distribution that is completely uniform to one that is concentrated on the bulk or more in the center, to a distribution that is in one of these corners of the triangular, or to a distribution that is in the edges of the triangular. This is an extremely important distribution, right? Because there's no other way you can get this. You know, if you want something that happens on the extremes, right? This is a right scenario. If you want something, you have prior information that this should happen in this corner. This is important information. If it is uniform, of course, this Dirichlet one process, distribution will be what you need. But the way, especially for people in computer science, in addition to this Dirichlet distribution, things can get more fancy because there is a Dirichlet process, okay, which is a distribution over probability measures, and that has a lot of implications on many research topics today. Has a lot of applications. And so it is sort of a generalization of a distribution, but it is a process, okay? So I don't believe we will do this in this semester, but keep that in mind when you search on the web. Okay, and samples from a 5-dimensional Dirichlet distribution, with parameters, I take all the coefficients to be 5. So these are the samples. And again, I advise you to actually play with this and open these files and look to see how you sample from a 5-dimensional Dirichlet process, this Dirichlet distribution, okay? If you change the coefficients alpha, you can see, you remember when the coefficients are very small, most of the samples are in the edges. That's why you see more samples being on the edges than in the bulk, okay? So this is important. Means and moments and all of these things are given in the notes. All right. I keep forgetting. When do we finish? At 4:30 or 4:45? 4:45. All right. It's Friday. Come on. We don't have anything else to do, right? So let me, I'm going to give you, a little bit about some inequalities that are true for any distribution, and in some sense they're amazing inequalities, but they're often used in the context of Monte Carlo simulation. So it's a good idea to see these calculations today. So the first inequality is what is called the Markov's inequality. So let's read it. It says, if x is a non-negative random variable, for any alpha greater than 0, the probability of x being greater or equal to alpha is less or equal to the expectation of x divided by alpha. Now, the derivation is basically this line here. There's nothing else, okay? But if you take this, and I'm not going to take you through the calculation, all right? I'm going to show you with basically whatever you see on this slide, a derived result that says the following. The probability of x being away from the mean of x by a distance greater than epsilon is always less or equal to the variance divided by epsilon. For any distribution, you have to think about it, right? Because it's a sort of, it sounds something that comes out of the skies, but it's really sort of a trivial derivation in, this equation here, and then using particular things, this can also be applied for any function f of x the same way, and using that function to be what you see here, you get this nice Chebyshev inequality. So let me rewrite this so I can get you thinking a little bit here. And I'm going to rewrite this by redefining this variable, this parameter epsilon here, which can be anything. So I'm writing this as the probability of x being away from the mean of x by a distance greater or equal to epsilon times the standard deviation is always less or equal to 1 over epsilon squared. And you know what that means? The probability of being away from the mean by 2 standard deviations is less than equal to how much? 1/4. This is a universal result. All right, it's not like for a Gaussian or for this distribution or for that. This is for any univariate distribution. Basically, the probability of being away from the mean by epsilon times the standard deviation less or equal to 1 over epsilon squared. Okay? Extremely important result when you play with samples from distributions, right? And you're interested to calculate the probability of certain events. Okay, the law of large numbers, extremely important. So I'm going to put all of these things up. So let's say we have any distribution. So what I'm talking about univariate random variables, you can generalize this to anything. But let's say we have some distribution with a mean mu and a variance sigma square, and you take independent, identically distributed samples from that distribution, which we call them xi. So this is what we define as the sample mean, 1 over n, the sum of the samples. Okay? So you can show basically this is a random variable because these are random. So the mean of the sample mean comes to be mu. The variance comes to be sigma squared over n. Okay? And here are the two important laws of large numbers. So this tells you that as n goes to infinity, the probability of being a distance epsilon away from the mean is 0. This is extremely important result because it will be used to quantify convergence, of estimators and things like that. But here, if the estimator is an estimator to the mean of the distribution using the sample mean, it tells you the probability of this being greater than epsilon when n goes to infinity is 0. All right, so this is what is called the weak law of large numbers, but you can write this that almost surely that the limit of the sample mean is mu, all right? And this is the strong law of large numbers. I mean, when you talk convergence, if you take a rigorous course in probability theory, you will see that it's not just a matter of language, right? It makes a difference in which way you converge. This is different type of convergence by convergency probability, okay? But for us in this class, the important thing is that this converges to mu, all right? And this is a result of the law of large numbers. For any distribution, this is very important. So let's do an example of the law of large numbers. So suppose that you have n samples from a multivariate Gaussian, and somebody tells you go and estimate the mean and the variance. All right? So again, we draw samples from a multivariate Gaussian. I mean, we don't draw, let's say we don't know that's a Gaussian, but we want to fit a Gaussian. So you can think this another way. You want to fit a Gaussian, and you say, what will be the best estimate I can use for the mean and the variance, okay? So how do we estimate the mean? You remember, if we take the sample mean, as the number of samples goes to infinity, that's an excellent approximation to the actual mean of the distribution. So the sample mean can be written as such. All right? Can I do the same thing for the variance? Can you estimate the variance with samples? All right, so let's see what, obviously this calculation I mentioned for the mean of x, right? The same thing is true for a function of x. And the variance is a function of x. The only problem with the variance, you know what it is? The variance is defined with respect to the actual mean of the distribution. So we're going to have to do two approximations. One approximation, we will approximate the actual mean with the sample mean, and then we will use the law of large numbers for this function here, so we will write it like that. So we're committing sort of two mistakes that we will come back to discuss them later on. One is, of course, the Monte Carlo error, this approximation that you see here from the law of large numbers, and that I will show you in a slide what the error is, and then, of course, approximating the mean with a sample mean. But you can do this sort of in a justifiable way for any sort of distributions. So let's generalize this, and hopefully the equation on the bottom is what we need. So if you put all of this together, you remember the sample mean, we computed the mean, we said is mu, and the variance is sigma square over n. Sigma square is the exact variance, n is the number of samples. So you can basically, the central limit theorem shows that xn is a Gaussian with a mean, the actual mean mu, and a variance sigma square over n. So when you take samples, you converge to mu, and the error you do is sigma over square root of n. Okay? So this is very important, because how about if I ask you, how many samples do you need to compute the mean so that the error is less than epsilon? What will you do? For any distribution. Right? Remember, for any distribution, because the samples can come from whatever distribution you want, but the sample mean is a Gaussian. Miracle. That's why we like Gaussians, right? It's not an accident, but this comes from anywhere. So if I ask you how many samples do we need to get an approximation of mu to order epsilon, how will you compute that? I'm going to go and show you somewhere. Do I have this calculation? Yes. All right? So the calculation that I want you to study, that estimate is that n has to be greater or equal 4 times sigma square over epsilon square. And sigma square, of course, is the sample variance because we don't really know the exact variance. So the number of samples to have your approximations on mu less, to an order epsilon away from the actual mu is this nice number that you see up here, and this is the result of the central limit theorem. So very handy calculations for any distributions. If this comes to be 10 million, you're in trouble, but hopefully that will not be the case. So let me show you some results here. You remember we said if you draw samples from any distribution, the sample mean looks like a Gaussian, all right? So if the sample mean defines as an average, let's say, of 5 samples or 10 samples, notice that progressively for any distribution you approach a Gaussian. Okay? So you can draw samples from any distribution, and I think somewhere I even had I thought I had somewhere from a uniform distribution. So from any distribution, if you take the sample mean and you plot a histogram, you get a Gaussian. So let me do the following example of this approximation coming from this discussion of the law of large numbers and the central limit theorem. I want to calculate. I haven't really said anything about Monte Carlo. This is, it is really Monte Carlo. We will spend weeks on the topic. But suppose you want to compute an approximation of pi. Just, so we can finish the Friday on a good note. We want to compute an approximation of pi. So here is my calculation. Do you agree with me that this is the indicator function that x squared plus y squared is less than r squared. The integral is from minus r to r. So this is a box minus r to r, here r equal to 2. Do you, yes, the box is from minus 2 to 2, that, but this is a circle, this circle, all right? So what is this integral gives you? It gives you the area of the circle, which is pi r squared. We agree? All right. So what I'm going to do is, pi r squared. So pi is 1 over r squared of this integral, all right? And what I'm going to do is, I'm going to plug into this integral the probability of x and probability of y, assuming that x and y are uniform variables on the interval minus r to r. So if they are uniform, what's the probability of p of x? 1 over 2r, and what's the probability of y? 1 over 2r. So that's why I plug in a 4r squared there. So what is this integral now? Look at this integral. Don't you think this integral, it is the mean of these indicator functions under the joint probability distribution defined as p of x times p of y? Obviously the way I wrote it, x and y are independent, but who cares, right? But this is really the expectation of this indicator function under this uniform distribution in x and y. Do I know what to do? Okay, the r squared cancels, so I get a 4. Do I know how to calculate the expectation of a function? Of course I know how to, we discussed this, is 1 over n times the samples, where this indicator function is basically 1, which means the samples that they're inside the circle. So if you start sampling uniformly on the square, and you only keep the samples that they are inside the circle, and you do this calculation, you can get pi to any accuracy level that you're interested. Now, you may say, well, pi, who cares? Well, but this calculation also tells you that you can do integration in very high dimensions with Monte Carlo. And lots of people in physics, for example, they still do lots of calculations with Monte Carlo because they are much better and easier to implement than using sort of cubature techniques and the like. Okay? So let's see what we can do in a few minutes left. All right. Actually, I have 5 minutes. This is an amazing time. All right. So you will read everything that says there, so I'm going to only tell you the buzzwords in 5 minutes. So I am going to define the entropy of a continuous random variable as minus log of P of x. Okay? The physical meaning, again, it's 4:40, so we need to finish, and maybe we'll come back a little bit on Monday. So we're going to define the entropy of a continuous random variable as minus log of P of x. Now, you can think of the entropy as the amount of information that I gain when I observe x, or the amount of surprise that I get when somebody gives me a sample of x, which means that I anticipate that a variable, a random variable x that is picked, so basically a delta function like random variable, we have what type, big or low entropy? Low entropy, because if something is deterministic, I'm not surprised with it, okay? But if it is uniform, then the entropy will be high. So this is the definition, basically, of the entropy. Going fast here, we basically have to average of this, what you see here, with the distribution P, the underlying distribution of x, right? So if you take, so the entropy is actually the average of the log of P of x with respect to P of x, okay? So I'm going to bypass this slide. This is a physics perspective. So here is sort of two distributions. You can see this is more picked, has less entropy than this is that is, distributed more in x. Now, the maximum entropy concept tells you basically how to compute distributions that maximize the entropy. And so without doing any calculation, if my distribution is discrete, can you guess which distribution has the maximum entropy based on what we describe as motivation for defining the entropy? So if I have a discrete, over, let's say, k states, random variable, which distribution has the maximum entropy? You mean a uniform distribution, exactly. And the probability basically that the entropy of that distribution is going to come up to be the log of the number of states that you have in that distribution. So and actually the derivation on this for uniform distributions is given here, where I use a normalizing factor to be sure that P of xi is enforced to be equal to 1. Now, for a continuous distribution, we already discussed this. This is the definition of the entropy, the average with respect to P of x of log of Px, okay? So if somebody asks you, what is the maximum, what's the distribution that has a maximum entropy when you want to constrain these distributions to a fixed mean and a fixed variance, if you follow the calculation that is shown here for a univariate distribution, and also you can extend this to a multivariate distribution, it comes out that the Gaussian has the maximum entropy. So from all distributions, they have the same mean and variance, but they're sort of as random, as uncertain in all other degrees of freedom. The Gaussian is the one that satisfies those constraints, and that's why it also goes as, as a maximum entropy distribution. I want to discuss in the 1 minute that is left, an extremely important entity, which is a distance between two distributions P and Q. Now, why do we care about the distance of distributions? Because often we want to approximate a very complicated distribution with something simpler, let's say a Gaussian. So we would like to know how well we do in that approximation, and this Kullback-Leibler distance is what is used, all right? And is very much related with entropy, but right now let's use this definition, is minus P log of Q over P. So it's basically the log of Q over P averaged with the distribution P of X. It is not a true distance, okay, it's not a true distance, but it's greater or equal to 0, and it is equal to 0 when the distributions P and Q are equal, okay? And I have to tell you it is not symmetric. So actually we will see possibly in this course for certain approximations, if we use a distance between P and Q, we will get one set of algorithms. If we use a distance between Q and P, something completely different. Okay, so I'm going to come back to the slides because there are some critical things I wanted to tell you, including Jensen's inequality and about mutual information, which will be a nice criterion to define independence between random variables. So have a good weekend, and I'll see you on Monday. You're on the video.
Yeah. Registered for the class. Is it okay if I sit